Continuando con el panel tecnológico de las presentaciones del Seminario Internacional Lithium en la región de Sudamérica, a continuación lo invitamos a Teague Egan, quien es Chief Lithium Extractor de EnergyX, quien debatirá sobre la temática de Future of Lithium Production. Teague Egan es el fundador y director ejecutivo de EnergyX, responsable de todos los aspectos de la construcción de la empresa en el líder mundial de tecnologías de energía renovable. La experiencia de TIC es de emprendimiento en serie, inversión, invención y filantropía, y ha estado invirtiendo en activos energéticos del sector público y tecnologías sostenibles desde el año 2013. TIC, the room is all for you.
Thank you, Alejandro. Really appreciate the introduction. Thanks everybody for coming out. I can't really see how many people are here watching this, but for everybody that is, I appreciate your time. I'm going to run you guys through a little quick presentation for EnergyX and show you guys what we've been working on for the past 2 years. So we all know lithium demand is rising, but the question is really by how much, and how much new technology is needed by the existing lithium producers. How much more capacity do we need to bring online? And I always think that this chart is pretty interesting. It's a chart that Albedo Estimates. And on the left here, you can see where the estimates were for successive years within the past 5 years. In 2015, they thought that the 2025 estimate would be about 380,000. Then in 2017, they thought it would be about 500,000. In 2018, they thought it would be 800,000, and this is all by 2025. And then by 2019, they gave a range of about 1.3 million to 900,000. I think what's interesting about this is that each year they keep increasing their forecasted estimates for 2025. And now we're sitting here about to enter 2021, and we can only think about what it could be for 2030. So the estimate is steeply, dramatically rising. Now, what's the answer to that increase in demand and that supply-demand gap? Originally, I thought the answer was direct lithium extraction, and that's why we started EnergyX, to provide a new way for lithium production companies to bring on added capacity, to go from that 300,000 to 1 million, 1.2 million. But as we started developing our technology and we started talking to existing lithium producers, what we realized is that they have way too much existing capital that's invested in existing infrastructure to just get rid of that and try something new. It's way too big of a risk. And, I started asking myself the question, why wasn't direct lithium extraction from all of the existing companies that were in the space before EnergyX making headway? Why weren't we seeing, an Albemarle pilot plant with X direct lithium extraction company, or SQM testing out this technology in the field? And what I came to realize the answer was exactly what's on my screen. The companies that are producing lithium have too much invested in the conventional methods to try something that is a complete 180 and totally different. So I started comparing what direct lithium extraction was focused on to where EnergyX felt we could enter the market most efficiently. And these are how I broke it down. Direct lithium extraction focuses on greenfield technology, something that doesn't exist in terms of evaporation ponds. It's a replacement for evaporation ponds. A complementary technology is brownfield, something that works with evaporation ponds. Direct lithium extraction is probably focused towards junior miners, just because of the reason that major producers already have brownfield operations. Direct lithium extraction technology treats the feed brine as opposed to working with the evaporation ponds coming in mid-pond sequence. And as you start relating those factors to what that means for the capital expenditure, direct lithium extraction is a major capital expenditure. You're talking about in the hundreds of millions to replace existing pond infrastructure with an ion absorption or ion exchange or solvent extraction. For a complementary technology, you can bring something in that now only treats 1/30th the amount of feed brine, therefore vastly reducing the capital expenditure. You only have a very little amount of brine going through your system. And what that meant for EnergyX is that it's something that it's easy for the existing producers to try out. It's the quickest value add and quickest revenue generator for them to increase their recovery rates. And as you look at the scope of all the existing direct lithium extraction companies, they all claim the exact same thing. We increase recovery rate from 30 to 90%. We barely use any fresh water. We don't have reagents. Like, I've been watching a lot of these presentations, and basically every direct lithium extraction company says the same exact thing. The question is, how do you get there? And that's where we're trying to differentiate ourselves. So by coming in mid-pond sequence, we have lower CapEx. Our CapEx for a typical 20,000 per annum production would be roughly 8 to 15 million. And that can increase recovery rates from 30 to 90% effectively. So we fall in this complementary technology sector with our first products to market, where the other direct lithium extraction companies are really focused on ion exchange, ion absorption, solvent exchange. They fall in these categories. So major CapEx. It is great long-term potential. I can't deny that if you get to the point where you can prove it out and limit the risk. But they treat the feed brine. Maybe they're working with major producers at some point when those major producers are willing to take the risk, but these are all greenfield projects. So what EnergyX's complementary technology looks like is this. We insert ourselves mid-pond sequence, typically after the third pond. And the reason that we come in at this point is we want to come in right before the lithium magnesium co-precipitation. Now, if you look at brine compositions between Chile, Argentina, and Bolivia, the three countries that make up the lithium triangle, they all have somewhat different brine chemistries. We're typically focused on high or mid magnesium brines, which is not that prevalent in Argentina, but there is still some. So we want to come in right before the lithium magnesium co-precipitation. The ponds are actually very effective in what they do. The ponds use very little energy because they use the sun. They do a great job in evaporating H2O, and they do a great job of precipitating some of the earlier halides and sylvanites, the sodium chloride and the potassium chloride. And even in the carnallite pond, they do evaporate a lot of the magnesium chloride. It's just when the magnesium starts to evaporate or precipitate with the lithium is when you start seeing the highest lithium losses. So we insert our technology directly before that point. So we're able to utilize the first three ponds. And now we're only treating, as I mentioned before, about 1/30th of the initial feed brine. And that's why our lightest technology is such a lower CapEx than some of the other DLE solutions that are being proposed. Now, what our flow sheet looks like is this. So you have your typical DLE flow sheet, which is some sort of ion exchange or ion absorption or solvent exchange. It's matched with nanofiltration, reverse osmosis, and thermal mechanical evaporation. For us, we keep the existing ponds. We insert our lightest Gen 1 using electrodialysis. And I'll talk about this a little bit later, the trade-off between water and energy. And then we have a lot lower mechanical thermal evaporation. So you can eliminate these three things essentially with just one thing here. And that's kind of our typical Gen 1 flow sheet. And I'll explain Gen 1 versus future generations in a moment here. So what our technology is, we sought out some of the brightest membrane and nanotechnology engineers to make what's called a mixed matrix membrane. And we work with CSIRO, which is the Australian National Laboratory System. We also work with the University of Texas and the Materials for Water and Energy Technology Center. It's a DOE-funded laboratory directed by Professor Benny Freeman at the University of Texas. And we also work with the University of Oslo in Norway and a spin out from there called ProfMOF, which is the world #1 metal organic framework laboratory. And we use those three people along with some of our commercialization partners, including Membrane Technology and Research, to make a mixed matrix membrane that's highly efficient in separating lithium from magnesium. The separations that we've shown on real brine from South America is 125-to-1 lithium over magnesium. So 125 lithium ions pass through for every magnesium. We are able to customize our mixed matrix membranes to specific brine compositions. Some of the factors including the type of metal organic framework we put in, the weight percentage of metal organic framework, the porosity of the polymer, the adhesion factor, and what these mixed matrix membranes are. They're highly interconnected percolation networks of metal organic framework nanoparticles. They're held together by chemically, thermally, and mechanically resistant polymer. And this is essentially what we've been working on for the past 2 years, building something that has high separation of lithium magnesium. It has high flux or permeance so that the brine can flow through at an acceptable rate. And it has high stability so it lasts for hundreds or thousands of hours, which is the point we've gotten to in the laboratory, with no degradation. What the current mixed matrix membrane that we have formulated does is it separates the larger divalent ions. So in addition to magnesium, we separate calcium and sulfate. We're still working on the next generation, which is generation 2 that I'll talk about, that is a monovalent separator. So it separates lithium from sodium and potassium. A quick breakdown of what the nanoparticles are in the metal organic frameworks that go into the mixed matrix membrane. Basically, this was the original science that came out of Australia and Texas that showed these separations with single channel metal organic frameworks. So you have lithium magnesium separating at 1,500-to-1. You have lithium over calcium at 500-to-1. Lithium sodium at 1,000, and then you have these other separations that aren't really relevant to our lithium separation, but this was kind of the fundamental research. These nanoparticles have been produced by the kilogram of the day, so it's readily available when we reach the piloting stage. The apertures in the metal organic frameworks can be customized. So that's the next generation that we're working on, this putting this MOF, it's a different type of MOF, into the mixed matrix membrane format. So water versus energy. As we developed our mixed matrix membrane that's done now, we needed to figure out the most efficient mechanism of transport, how we wanted the brine to flow through. The two options, well, there's three options. One was pressure, which is how reverse osmosis works. And we canceled that out quickly because the osmotic pressure would deteriorate the membrane similar to nanofiltration. That's why you can't use nanofiltration on very high salinity brines. The second two was a concentration gradient, so similar to forward osmosis, but that uses really high water. You need a lot of water for that, which is scarce in these regions. So the mechanism of action that we're using is electrodialysis. And we force the brine through our membrane using an electric potential. And the cost of that is it's a little bit less than $100 per metric ton of energy costs. So that's really efficient for a lot of these lithium producers. So as I've talked a lot about generation 1, I wanted to briefly touch on generation 2 and generation 3. So I think everybody here understands generation 1. Generation 1 fits in mid-pond sequence. It's the one of the main contaminants. Generation 2 fits up into the feed. So when we start being able to efficiently separate lithium from sodium and potassium, we'll use generation 2 as a predecessor to generation 1 and run that in series. Generation 3 here fits at the end, and this is our solution for direct to lithium hydroxide. So it's a conceptual process that we've thought about to eliminate the lithium carbonate plant. It has to do with an ion exchange step, putting a hydrogen in to eliminate the lithium chloride. And I'll get to that. Well, actually, I won't get to that. But so this is Gen 2. Now, initially, our Gen 2 will work with some of these DLE companies that have talked earlier today. You put the ion exchange, ion absorption step to replace the ponds. And then this is supposed to be a 2. I'll fix that when we send out the presentation. This is our Gen 1 solution. So if you pair our lithium magnesium separation membrane with ion exchange, so our Gen 1 already replaces nanofiltration, reverse osmosis, and evaporation, and then you just move this ion exchange down here and pair it with us. Eventually, when we do create our monovalent separation, we will pair our Gen 2 lithium sodium or lithium potassium separation membrane with our Gen 1 membrane. And that is the presentation for today. My email is here and ready for questions. And I hope I was on time.
Yes. No, yes. Thanks, Teague. We have a couple of questions for you here. The first one, you presented a very good selectivity with magnesium. The question is, what about boron? Presentaste una muy buena selectividad con el magnesio. ¿Qué respecto al boron?
Sorry, could you repeat that question? I couldn't quite hear.
You presented a very good selectivity with magnesium. What about boron?
What about boron? What about boron? The boron is a very small, it depends what form the boron comes in. As you know, there's a lot of different forms of boron. That's dependent on the brine chemistry of the particular region. I know that we have been working on boron selectivity, and I think that will be ready with our generation 2 membrane. It's monovalent selective. But I will have to check with our technical team on boron lithium separation. So whoever asked that question, just shoot me an email and I'll get you a more specific answer on that.
Thanks, Teague. And there is a second question for you. Do you have demo or pilot scale trials for this technology for pre-concentrated brine? ¿Tienes pruebas a escala piloto de demostración para esta tecnología para salmuera preconcentrada?
Yes, so we do have lab pilot sized equipment that can run up to 150 liters per hour of brine. If typically what we do with the existing producers that we're working with, and at this point we're pretty much working with several of the top lithium producers. We actually just announced our Orocobre collaboration, but we typically start with 50 liters of brine to test it on smaller permeation cells. And then we ask partner producers to send us 1 to 5 metric tons per sample of brine that we test on our lab pilots that can do 150 liters per hour. From there, we send pilots either that size or slightly larger into the field in containerized units to test on site.
Thanks, Teague, for your presentation. Your email is here, so any question will be sent to your email. Muchas gracias, Teague, por la presentación. Ahora vamos a un break de 15 minutos y retornamos con la última serie de disertaciones técnicas. Teague, thanks in advance.
Thank you very much, everyone.